So what are the forces acting on our block at the bottom? Tension up, gravity down. Okay, looks good. Now if you were just to see this all by itself, what would you think is true about the tension and gravity? Yeah, it looks like they're going to be equal. Okay, it looks like they're going to be equal. However, they're not, because what's happening? There's a velocity. Yeah, there is going to be a velocity here. So when we set up our equation, we're going to have tension minus mg equals ma, but this is not at a equals 0. When a is equal to 0, like if you're just hanging this mass by a string, then a is equal to 0, and therefore they're equal, right? However, if it's moving, there's definitely an a going on. And in this case, it's a little more complicated because there's a angular a, because it's accelerating it downwards. But at this moment in time, there's also a centripetal a that's changing its direction, pulling it up. And that's what we're looking at is right here, the centripetal a that's going to pull it upwards. MAC, yeah. Okay, and so notice here, what's going to happen to the t? How's it going to compare to just the weight? Is it going to be larger, smaller, or the same? Larger, yeah, it's going to be larger. And notice here, you can see that in the equation, mg plus mac. Okay, at this point it should be pretty easy. We're just going to go ahead and substitute in some numbers. Can we cancel the mass? Nope. So we're going to go 2 times 9.8 plus 2 times v squared over r, right? AC equals v squared over r. So 1.98 squared. Is our radius 50 centimeters? Or do we have to do some weird cosine sine thing? It's 50 centimeters. Yeah, it's still 50, right? This is the length of the string. This is the circular motion that we're making. So we are going to convert that though, so 0.5. And what's the answer? Okay, and if it was just gravity, if it was just the weight, it would have been about 20, right? And so it's more. It's going to be a greater tension.